All right, section 11.5, proportions with area. So this lesson actually builds off of a homework question that we had on a previous worksheet. And we actually talked about what this lesson is about when we went over that homework question. But we're going to get into it a little more in depth with a bunch of examples of the conjecture that we're going to take a look at. So we start out with this example. We're being given two triangles, and we're being asked to find the ratio of the corresponding lengths and the ratio of the areas. So let's take a look at the ratio of the corresponding lengths. Well, this is pretty simple. The height of the small triangle over the height of the big triangle, 3/9, which reduces to 1/3. The base of the little triangle over the base of the big triangle, 8/24, reduces to 1/3. Now let's look at the ratio of the areas. We know area of a triangle, 1/2 base times height. So area of the little triangle, 1/2 times the base, that's an 8, times the height. 8 times 3 is 24. 24 times 1/2 is 12. Area of the big triangle, 1/2 base times height. 1/2 of 24 is 12. 12 times 9 is 108. So if we take the area of the small triangle over the area of the big triangle, we have 12 over 108, which reduces to 1/9. Now the question is, what is the relationship between the ratio of the corresponding lengths and the ratio of the areas? So we take 1/3, which is the ratio of the corresponding lengths, and if we squared that ratio, we'd end up with the ratio of the areas, 1/9. Now let's just see if this is coincidence or if it holds true for circles. So we're given two circles, one bigger than the other, one with radius 3, the other with radius 2. And we're being asked to find the same things, the ratio of the corresponding lengths and the ratio of the areas. So the ratio of the corresponding lengths, in this case it's the radii, smaller over bigger, 2/3. Ratio of the areas, formula for area of a circle, pi r squared, right? So we have pi times the radius squared for the big circle. That will give us 9 pi. We have pi times the radius squared for the small circle. That will give us 4 pi. Take the smaller area over the larger area. Of course, the pi's are going to cancel out and leave us with 4/9. We see the same thing happening here. Because if we take the ratio of the lengths and we square it, 2 squared is 4, 3 squared is 9. We end up getting the ratio of the areas. So this is what we call the proportional areas conjecture. If corresponding side lengths of two similar polygons or the radii of two circles compare in the ratio of m over n, then their areas compare in the ratio m squared over n squared, or the quantity m over n squared. So here's a visual of that conjecture. It says the reason behind the proportional areas conjecture is that area is a two-dimensional measure. Notice in the diagram at the right that the sides of the larger triangle are 2 times those of the smaller triangle. Yet the area of the larger triangle is 4 times that of the smaller triangle. Because the area of a triangle is related to the product of the base and height, when both dimensions are doubled, the area increases by a factor of 4. So the question is now, does that same conjecture apply to 3-dimensional objects? We certainly saw that it applied to 2-dimensional figures. What about 3-dimensional figures? So 3-dimensional figures don't have an area, they have a surface area. So we're going to go through a couple examples, do the same thing, find the ratio of the corresponding lengths and the ratio of the surface areas. So we have two rectangular solids here. Lengths, so let's see, this is 3, 2, and 1. And 6, 4, and 2. Ratio of the corresponding lengths is 1/2. All right, now we have to find the ratio of the surface areas. All right, so surface area of the smaller figure, 22 units squared, right? Just count up the number of units on top, on bottom, on left, on right, on front, on back. We get 22 units squared. Surface area of the bigger rectangular solid is 88 units squared. So now we can find the ratio of the surface area, smaller to bigger. 22 over 88 reduces to 1/4. Now, does the previous conjecture hold here? Certainly does. If we take 1/2 and we square it, we get 1/4, right? Same as the ratio of our surface areas. All right, last example to look at. So we have two spheres, 3-dimensional figure. Let's see if the conjecture holds. We have the radius of the smaller sphere is 3, radius of the bigger one is 9. Ratio of those corresponding radii would be 3 over 9, or 1/3. We have to calculate the surface areas of the spheres. 4 pi for the small sphere, radius squared. 3 squared is 9. 9 times 4 is 36. That's 36 pi. For the big sphere, we'd have 4 pi r squared. 9 squared is 81. 81 times 4, 324 pi. So we take the ratio smaller over larger, 36 pi over 324 pi. Pi's will cancel out. 36 over 324 reduces to 1/9. And so we see once again that the conjecture holds, right? Because if we take the ratio of the corresponding radii and we square it, we're going to get 1/9, which is the same as the ratio of the surface areas. So the proportional areas conjecture not only applies to 2-dimensional figures with area, it applies to 3-dimensional figures with surface area as well. This is the same conjecture, just reworded slightly to apply to prisms and spheres, which are the 3-dimensional figures.